Okay, Amon is here. Darcy is here. Bishop, Bragg, Caudill, Chestnut, Fullwood, Erlinson, here. Gerard is here. Green, Kennedy, Leonard, Mohammed Boy is here. Spall is here. Solomon is here. Switstack. Okay, so let's continue our discussion of thermochemistry. And the next thing we're going to talk about is how do we actually measure heat flow in order to determine, for example, the amount of heat that is lost or gained in a chemical reaction. And this deals with an area which is called calorimetry, right? Calorimetry is basically how we measure heat flow. And there are different, well, before I say that, the instrument that is used for this purpose is known as a calorimeter. And there are different types of calorimeters of different levels of sophistication. The ultimate in the low-tech variety is simply two coffee cups nestled in each other, right? The cups are made of styrofoam, so you know it's insulated. So there's no exchange of heat energy between what's happening inside the cup and outside, right? So basically, this is how we put it together. You stopper it, you have two holes in the stopper. One hole you're going to push through a thermometer to measure the temperature change, and through the other hole, you're going to put a stirrup, all right? And that's basically the makeup of the coffee calorimeter that is used to measure the amount of heat generated or absorbed in a chemical reaction. One that is more sophisticated is what is called a bomb calorimeter. And this is used particularly when it comes to measuring the heat of combustion, the amount of heat that is released when an organic compound is burned in oxygen, right? And this is a diagram which shows you what it looks like. It consists of this, what we call a steel bomb, right? And you have a compartment here where you put your organic substance. You have two electrical wires leading into it, and this is connected to an external circuit. When you switch it on, then basically this starts burning. And then what happens is that the heat generated here is transferred from inside the bomb into the water here, right? So basically, you're going to measure the temperature rise of the water. And then there's this propeller kind of device, which is basically used to make sure that the heat is evenly distributed throughout the water so that you can get the correct temperature measured, all right? So that's basically a more sophisticated type of calorimeter, which is used to find the heat of combustion of an organic substance. All right. Okay, so that's basically, you know, all I'm going to say about instrumentation. So let's talk about how we can use it to measure the amount of heat that is either generated or absorbed in a chemical reaction. First thing we need to make mention of is the relationship between the heat change for the reaction and the heat change for the calorimeter, right? So as stated here, the heat that is involved I must apologize to you guys out there in Zoom. I don't think. Oh, okay. I thought I made an error. Okay, so as I was saying, the heat that is involved in the reaction, let's say the reaction is exothermic, that would be equal to the amount of heat that is absorbed by the calorimeter. So I could represent that in a simple equation which says that Q of the calorimeter will be equal to minus Q of the reaction, right? So basically, whatever the amount of heat that is generated by the reaction, let's say, then that will be equal to the amount of heat that's absorbed by the calorimeter, or vice versa, all right? So that's the first thing we need to understand about the relationship between the heat change of the calorimeter and the heat change of the reaction. The next thing we're going to say is that what we do as far as the calorimeter is concerned, to determine the amount of heat change occurring for the calorimeter is that we determine the temperature change, right, of either the water or the solution that is involved in the reaction, so that we can determine the amount of heat that is absorbed or produced in the reaction, right? So here now I'm going to define a term which you may not have met before, the heat capacity of a system. This is the amount of heat required to change the temperature of the system by 1 degree Celsius or 1 Kelvin, right? So basically, this is the formula for calculating the heat capacity. Uppercase C is equal to Q, and remember now, Q can be either negative or positive, right? Divided by delta T, which also can be either negative or positive, right? So that's C, right? And the units of C, the heat capacity, are joules per degree Celsius, or, write this down, or joules per Kelvin. And it doesn't matter which of those units you use, your numerical value will still be the same, all right? So that's the heat capacity. The molar heat capacity, which is something that, to be perfectly honest, I don't anticipate you using this, but I'll give you anyway. It's the heat capacity of 1 mole of a substance, right? So basically that's the molar heat capacity, and that's all I'm going to say about that. What I will talk about more extensively is the specific heat, right? And this is the heat capacity of 1 gram of a pure substance, all right? Or a homogeneous mixture, depending on the type of reaction we're talking about, all right? So basically, this is how we determine the specific heat. By the way, the symbol for specific heat is lowercase c, while the symbol for heat capacity is uppercase C, right? So it's important that you understand the difference between the two. So the specific heat, which is lowercase c, will be equal to the heat capacity, which is uppercase C, divided by the mass in grams. Now remember, uppercase C is equal to Q divided by delta T. So if we replace uppercase C with this, you're going to end up with this equation here, which can be rewritten as Q is equal to C times M times delta T. All right. So Q is the amount of heat change. C is the specific heat. M is the mass in grams. And delta T is the change in temperature. Again, the change in temperature can be in Kelvin or in Joule or in Celsius, right? But it doesn't matter which one you use, the results will still be numerically the same. All right. And I'm sorry. Delta T is the change in temperature. Change in temperature. And that can be in Kelvin or degrees Celsius, right? M, while I'm at it, M would be the mass in grams, and C would be the specific heat. Now the units of specific heat would be joules per gram degrees Celsius or joules per gram Kelvin. Again, it doesn't matter which of them you use, and Q would be in joules. All right, so those are the units for each of those terms in that equation. All right, so that's the relationship between the specific heat, the mass, and the change in temperature. Now C, the specific heat, is a constant for whatever the substance is. It's a physical constant, you know, kind of like in the same vein as melting points, boiling points, you know, different substances have different melting points and boiling points and so on, and densities. Well, different substances have specific heat values. In fact, I think there's a table on the next slide. Oh, no, it's not here. Maybe in a future slide. I'm going to show a table shortly which has different values for specific heat for different substances. But before we get to that, let's look at this example. So this question says, and well, okay, let's do the question first. This question says, calculate the heat capacity of an aluminum block that must absorb 629 joules of heat from its surroundings in order for the temperature to rise from 22 degrees Celsius to 145 degrees Celsius. All right. Now remember, when we talk about heat and work, we have to pay attention to how the question is worded so that we use the appropriate sign. Right? So if you notice in this question, the question says that the aluminum block absorbs this amount of heat. So what does absorb mean? it means that the heat is what? It's positive, right? So therefore, this is the equation we're going to use. Q is equal to M times C times delta T, which is the equation I just showed you, right? And the question is asking for you to calculate C. So that means that C would be equal to Q divided by M times delta T, right? So C would be equal to 629 joules because we know it's positive, divided by M, which is, oh shoot, I just made a mistake. The mistake I made is, let me just erase everything. The mistake I made is that I'm calculating the specific heat and the question is asking for the heat capacity, which is different. All right, so let me restart. So Q is equal to the heat capacity, which is uppercase C times delta T, right? So C is what the question is asking for, not lowercase c, uppercase C, which is equal to Q divided by delta T, right? So Q, as I said before, is 629 joules divided by the change in temperature. Remember, the change is always final minus initial. Final minus initial. So 145 would be the final temperature minus the initial, which is 22 degrees Celsius. So let's see what that gives. I'm going to work out the denominator first, 145 minus 22. So that gives, according to my calculation, that gives 123 degrees Celsius. And 629 divided by 123. So according to my calculations, and please correct me if I'm wrong, but according to my calculation, the answer is 5.11 joules per degree Celsius, and that would be the heat capacity. We'll just do this again just to make sure. 629 divided by. Okay, so that's what I got. All right. Yes, sir.
Is that like a line? See, that's
Q.
Q.
Oh, sorry. You mean this here? That's Q. Q is the symbol that we use to represent heat change. All right. Okay. Any questions about this example? Any questions? Any questions? Okay. Okay. So more things we need to say about specific heat. Let me just get rid of this here. Okay. So so that's equation. All right. And again, I'm emphasizing the science, right? When it comes to interpreting questions and how we use this equation and use the appropriate signs in this equation to do the calculation more accurately, right? So of course, if the change in temperature is positive, right? That means, of course, there's an increase in temperature. That corresponds to Q being positive, right? And therefore, heat is being gained by the system, right? If delta T is negative, then the opposite is true. That means that heat is lost by the system and Q is negative, all right? Now, there's some other units of energy that you might come across, which are not metric units. Calorie is one such unit. It's not a metric unit, but we have a relationship between the calorie unit and the joule unit, which is given right here. 1 calorie is equal to 4.18 joules of energy. And that information is available in the tables that I posted in Canvas, all right? So water, and this is the definition of the calorie unit, by the way. The calorie unit came about as a result of the properties displayed by water. Basically, it was decided that water has a specific heat of 1 calorie per gram per degree Celsius. So basically the calorie definition, it is the amount of heat needed to change the temperature of 1 gram of water by 1 degree Celsius. That's the definition of the calorie unit. And that's basically it as far as that is concerned. And it turns out it's equal to 4.18 joules in terms of the metric unit joules, all right? And then there's also what is called the nutritional or food calorie, right? And the symbol for that is CAL, where, or the unit I should say is CAL, where C is expressed as uppercase, or it can be expressed as kilocalorie, right? And that is equal to 1,000 calories. So this is basically the unit that is used in the field of nutrition when it comes to measuring energy. And this is the list I was mentioning before. So basically these are just different substances. and their corresponding specific heats, all right? And one thing I want to point out is that of all these substances, water has the highest specific heat of 4.180, right? And that is due to a phenomenon known as hydrogen bonding, which hopefully we'll get to later on in this semester. But what you'll find also is that metals tend to have, relatively speaking, low specific heat. So if you look at, for example, aluminum, copper, lead, aluminum has the highest of these, which is 0.902, and then the others are significantly lower, like iron and lead and mercury and so on, all right? Non-metals tend to have higher specific heat, and as I said before, water has the highest specific heat of almost any other substance. Okay, so let's look at some examples, and I'm gonna need some space here, so let me copy this question first and paste it onto a Word document. So this is the question. It says, how much heat in joules and in kilojoules does it take to raise the temperature of 225 grams of water from 25 degrees Celsius to 100.0 degrees Celsius? Now, you should be given the specific heat of water. So let me write that down right now. I showed you earlier, but if you're given a question like this, that value would have to be given. And in fact, I think that is also available in that table. So I'm going to check and make sure, but I'm almost 100% sure that it's there. Anyway, so the specific heat of water is 4.184 joules per gram degrees Celsius, right? So the question is asking for Q, which is equal to M times C times delta T. So M is equal to the mass, which is 225 grams, times C, which is the specific heat, times the change in temperature, which is, again, final minus initial always, right? So that would be times 100.0 degrees Celsius minus 25.0 degrees Celsius. And if we work out what's within the parentheses, that would equal to 75.0 degrees Celsius. And then we do the rest.
So when you have the 4.184,
Mhm.
is that being multiplied by the joules over the gram?
Those are the units, joules over grams degrees Celsius. Or Kelvin. You can replace the degree Celsius with Kelvin. But those are the collection of units. And you're going to see how it works out, because when you do the multiplication, the gram units will cancel out here and here. The degree Celsius will cancel out here and here. So the only unit remaining would be the joule unit in the answer. All right. So 225 times 4.184 times 75. And according to my calculations, when rounded out to 3/6, the answer I got is, and again, please correct me if I'm wrong, 7.06 times 10 to the 4 joules. And that's how that is done. All right. Any question about this one? Any questions? Scroll down here. Oh, we need that here for the examples.
So what are you putting in the numerator there?
Where,
Where you have the joules over grams degrees Celsius. You're doing 225 times the 4.184.
Times this, times 75. This 75 comes from this right here. The difference between the 100 and 25.
Are you doing the 225 times 4.184 divided by 75?
No, times.
Okay.
Yeah, times
Okay.
75. Yeah, times 75. Okay, any other questions? Any other questions? Oh, right, thank you. We need to convert this to kilojoules. So how do we do that?
Divided by 1,000.
Exactly, so we multiply by 1 kilojoules divided by 1,000 joules. And if you do that, you're gonna get 70.6 kilojoules. All right. Any questions about that? Okay, okay, why did I do that? All right, so let's go down here. In fact, let me go back to the PowerPoint and copy the next question. And let me paste it again down. Yes, right, please. All right, you know what, let me just get rid of all this here. So. Um. Okay, so here's the next question. It says, what would be the final temperature if a 5.00 gram silver ring at 37 degrees Celsius gives off 25.0 joules of heat to its surroundings? And it says use a specific heat of, oh, so we need a specific heat of silver. So let me look that up. That was in the table I showed you earlier. So the specific heat of silver is 0.235. So let me write that down here. So specific heat of silver is equal to 0.235 joules per gram Kelvin. All right. Okay. So we need that information in order to answer this question. So the question gives you the mass, it gives you the initial temperature, and it says it gives off 25.0 joules of heat. So gives off mean what? If it is losing heat, that means Q is what?
Negative.
Negative, exactly. All right, so you have to keep that in mind when you're answering this question. So let me just write down the equation here. The equation is Q is equal to M times C times delta T, right? Now the question is asking for the final temperature. So what we need to do is find out what delta T is first. So delta T is equal to Q over M times C, right? Now the question says, as I said before, that the ring gives off this much heat. So therefore, Q is going to be minus 25.0 joules divided by M, which is a mass, which is 5.00 grams, times the specific heat, which is 0.235 joules per gram Kelvin. So let's see what that gives. So that's minus 25 divided by 5 divided by 0.235. So according to my calculation, this works out to be equal to minus, how many sig figs? 3 sig figs. So minus 21.3 degrees Celsius. So that's a temperature change, right? So how can we use that temperature change to find the final temperature? And they gave us, by the way, the initial temperature. This is the initial temperature. I'm going to call that T1, the initial temperature, right? What the question is asking for is the final temperature, which is T2. So how would you find T2? Or let me ask you this. What is the relationship between T1, T2, and the change in temperature? The mathematical relationship between T1, T2, and the change in temperature. The change in temperature is equal to what? T2 minus T1. Okay, very good. The question is asking for T2, so therefore, T2 will be equal to what? Delta T plus T1, right? We already calculated delta T, which is minus 21.3 degrees Celsius, and T1 is 37.0 degrees Celsius. And that will give us the final temperature, which is what the question is asking for. So that's 37 minus 1.3. So according to my calculations, the final temperature will be 15.7 degrees Celsius. And that's how that is done. All right. Any questions about this? Any questions? Okay. Let me give you some time to write that down. This will get late. Okay, is Brad here?
Here.
Okay. Chestnut, let me check. Erlinson, not here. Green. Kennedy. Leonard. Switzak is here, okay. All right, so let's continue. Okay, so another example. All right, now this one is interesting. Let's read it. It says here that a 15.5 gram sample of a metal alloy is heated to 98.9 degrees Celsius and then dropped into 25.0 grams of water in a calorimeter. The temperature of the water rises from 22.5 degrees Celsius to 25.7 degrees Celsius. And the question is asking for you to calculate the specific heat of the alloy, all right? So let's think about what we have here, right? We have a metal alloy, which is at a temperature of 90.9 degrees Celsius, right? It's added to water. The initial temperature of the water is 22.5 degrees Celsius, all right? So obviously the metal is hotter than the water, all right? And if you remember what we said earlier, whenever you have two objects in contact with each other, right? The heat flow will go from the hotter object to the cooler one, right? So basically in this particular case, the metal alloy will lose heat to the water, right? And that heat flow will continue until both the metal and the water will be at the same temperature, right? So the final temperature of the water, which is 25.7 degrees, will be the same as the final temperature of the metal, all right? So basically the first thing I would write down here is the relationship between the heat change of the water and the heat change of the metal, right? And that relationship is simply Q of the metal is equal to minus Q of the water, right? Because whatever the amount of heat that is lost by the metal will be equal to the same amount of heat that is gained by the water, right? So as far as the metal is concerned, its heat change is negative. As far as the water is concerned, its heat change is positive, right? So that's the first thing I write down. And then if you remember, we said that Q is equal to M times C times delta T, right? That is true for any substance. So I'm going to write down a similar expression for both QM and QW, right? So in the case of QM, that will be the mass of the metal times the specific heat of the metal times the change in temperature of the metal. And that will be equal to minus the mass of the water times the specific heat of the water times the change in temperature of the water, all right? Now remember, the question is asking for the specific heat of the metal. So to isolate that over here in this equation here on this side, I'll have to divide both sides by the mass of the metal times the change in temperature of the metal, right? So that this will cancel with that will cancel with that, and here you're going to have mass of the metal times the change in temperature of the metal. So what we have to do now is to, based on this equation here, put the appropriate numbers that is given in the question into the different terms here, and that will give us a specific heat. So minus the mass of the water. What's the mass of the water?
25 grams.
25.0 grams, right? And the specific heat of the water, which would have to be given to you again, is 4.184 joules per gram degrees Celsius, right? Times the change in temperature of the water. Now, what's the change in temperature of the water? It says that the temperature rises from 22.5 degrees Celsius to 25.7 degrees Celsius. So the change in temperature of the water would be the final temperature, which is 25.7 degrees Celsius, minus the initial change, the initial temperature, which is 22.5 degrees Celsius, all right? So that takes care of the numerator part of this expression. And then down here in the denominator part, the mass of the metal. What's the mass of the metal? 15.5 grams. We're going to put that down here, 15.5 grams. Multiplied by the change in temperature of the metal. Now remember, the initial temperature of the metal is 98.9 degrees, right? And the final temperature of the metal is the same as the final temperature of the water, which is 25.7 degrees, right? So here we're going to put multiply by final temperature, which is 25.7 degrees Celsius, minus the initial temperature of the metal, which is 98.9 degrees Celsius. And that's basically the setup. So it's all a matter of now doing the number crunching. What I'm going to do is work out what's within the parentheses first. 25.7 minus 22.5. And according to my calculation, this part here works out to be 3.2 degrees Celsius. And then for the other part within parentheses, 25.7 minus 98.9. And according to my calculation, this part works out to be equal to minus 73.2 degrees Celsius. And then we do the rest, all right? So 25 times 4.184 times 3.2 divided by 15.5 divided by minus 73.2. So according to my calculations, the answer here rounds off to two sig figs, right? So the answer here would be 0.30, and the units would be joules per gram degrees Celsius, because these gram units will cancel out here and here. Degrees Celsius will cancel out here and here. So you're left with joules per gram degrees Celsius as your final unit. So this would be your final answer, right? Okay, any questions about this one? Questions? Okay. I gave you guys a copy of assignment 6 already, right? So, and I think we did numbers 1 and 2. Okay, so now you should be able to do number 3. Before I move from this, any questions about this? Any questions? Any questions? All right, let's do. Okay, so let's look at question number 3. It says a 1.0 gram sample of propane, and it gives you the formula. Is burned in a calorimeter. The temperature rose from 28.5 degrees Celsius to 32.0 degrees Celsius. And the heat of combustion is 10.5 kilojoules per gram. So the question is asking for you to calculate the heat capacity of the calorimeter in kilojoules per degree Celsius. So remember, the heat capacity is equal to Q divided by delta T, all right? So in order for us to calculate C, uppercase C, we need Q and we need delta T. Now delta T is easy to determine. That's the difference between the 32.0 degrees Celsius and the 28.5 degrees Celsius. So that gives you 3.5 degrees Celsius. And then, so now we need to find Q. So how do we get Q? The answer for Q lies in the fact that for every 1 gram of sample of the gas burned, the amount of heat released is 10.5 kilojoules. There's something I'm missing here. Let's see. Oh, okay. So here's the thing. Remember we said that Q of the calorimeter is equal to minus Q of the reaction, all right? So basically, for the calorimeter, delta T is 3.5 degrees Celsius, and Q of the reaction will be equal to 1.0 grams multiplied by 10.5 kilojoules per gram, right? So this will be equal to 11 kilojoules, all right? And since the heat of combustion is 10.5, that means that this will be negative, which would mean that Q of the reaction will be negative, which would mean that Q of the calorimeter will be equal to positive 11 kilojoules, right? So therefore, C will be equal to Q, which is 11 kilojoules, divided by the change in temperature, which is 3.5 degrees Celsius. Let's see what that gives. 11 divided by 3.5. So according to my calculation, this works out to be equal to 3.1, and the units here would be kilojoules per degree Celsius as required. All right. And that's basically how that is done. Yes, sir.
Next to the key. Or the left,
Here?
Yeah.
That's
a
1.0.
little more, like, what is the,
Here? It's a negative sign.
I was talking about what's underneath the.
Q reaction.
What's that?
Oh, Q reaction. The heat change of the reaction, I'm sorry. Okay, yes, sir. Because 10.5 times 1 gives you 10.5, but you have to round out the 2 sig figs. Right. You have 2 sig figs here, you have 3 sig figs here, so you have to round out the 2 sig figs here. All right. Okay, any other questions? You look puzzled, Miss. Because that's what happens when you burn something, it loses heat, right, exactly. So therefore, the amount of heat change as far as that's concerned must be negative. Okay, any other questions? Any other questions? Okay, so let's look at the next question. Now, in the next question, let me clear this first. Let me scroll down here. It says when 72 grams of a metal at 97 degrees is added to 100 grams of water at 25 degrees, the final temperature is 45. Okay, so this is very similar to the question that we did in the PowerPoint. So the question is asking for what is the heat capacity per gram of the metal, which is the same thing as the specific heat, right? So I'm just going to make one minor change to this question. I'm going to put a decimal point here to make this 3 sig figs. So please make a note of that, right? That's going to be 3 sig figs. Okay, so let me see what you can come up with in terms of answering these questions. And feel free to look at the example that we worked earlier. You have the metal, which is at a high temperature, added to water, which is at a lower temperature. So as I said before, the heat flow will move from the hotter metal to the cooler water. So what's the first thing you write down? You mean this? Okay, what next?
72 grams of the metal. Times
Nope.
the C of M, the
Right,
specific heat.
specific heat of the metal. You don't know what that is, that's what you're trying to find out. Times.
The change in temperature,
Okay, so what will be the change in temperature of the metal?
97 minus 25,
Are you sure about that?
no,
What's the final temperature of the metal?
45.5,
45.5 degrees Celsius. Minus the initial temperature, which is what?
97.
97.0 degrees Celsius. Okay. And that would be equal to what?
So the water, so 100 grams of water,
Okay. Multiplied by the specific heat of water, which is
4.184.
multiplied by the change in temperature of the water. So what's the, remember, the change is always final minus initial, right? So what's the final temperature of the water? Hmm? 45.5 degrees Celsius. What's the initial temperature of the water? 45 degrees Celsius. Now, there's one important thing that we forgot.
You have to divide.
Before we get to that. Yeah, right. Q of the metal is equal to minus Q of the water. So you can put a negative sign here or here, it doesn't really matter, but I'm gonna put it here, right? Okay, so as he just said, what you do next is divide. What did you just say? Divide.
Divide the mass, the change in temperature.
Celsius minus 97.0 degrees Celsius. So that this will cancel with this will cancel with that. And in fact, what I would do is also transfer the negative sign from here to here. And then do the same division down here, 45.5 degrees Celsius minus 97.0 degrees Celsius. And that's the setup. So let's work out what's within the parentheses first, 45.5 minus 25. So according to my calculation, this part up here will give you 20.5 degrees Celsius. And the bottom part here, 45.5 minus 97.0. So that part will give minus 51.5 degrees Celsius. Oh, I forgot to multiply by 72 grams here, very important. Okay, so we do the rest. So let me do the numerator first. 20.5 times 4.184 times 100, and then divide all of that by 51.5 negative times 72. So according to my calculations, and again, please correct me if I'm wrong, how many sig figs did I need to know? Okay, 2 sig figs. So according to my calculation, the answer would be equal to 2.3. And the units again would be joules per gram degrees Celsius. That's how you do that. All right? Any questions about this one? Questions? Okay, so scroll down here to see what's. Oh, this one is interesting. Okay, are we finished with this? Can I hear it? All right. So this question says, what is the resulting temperature when 35.0 grams of water at 75 degrees Celsius is mixed with 15.0 grams of water at 10 degrees Celsius? All right. Again, let me put a decimal point here for the 10 degrees. All right. Okay. So, and it gives you the specific heat of water, right? So, any ideas? You have hotter water being added to cooler water. So what do you think is going to happen? I'm sorry? Right, so therefore what I'm going to use, I'm going to say QH is the heat change for the hotter water, and QC is for the cooler water. So therefore QH is equal to minus QC, right? So it's the same principle as if we did the previous cases where you add a hotter metal to cooler water. All right. So for QH, the expression I'm going to write down is MH times CH times delta TH is equal to MC times CC times delta T C, right? So that, oh, and don't forget the minus sign, right? But guess what? It's the same substance, right? So the specific heats are going to be the same. So these two will cancel out. See what I'm saying? So basically what we have to do now is find out okay, what are we gonna do? Okay, so let's put the numbers in. The mass of the hot water is 35.0 grams times the change in temperature of the hotter water. Now, what's the change in temperature? It's a final temperature, which we don't know, TF, minus the initial temperature of water, which is 75 degrees Celsius, right? And that will be equal to minus the mass of the cooler water, which is 15.0 grams, times the change in temperature of the cooler water. Again, we don't know what that is, because we don't know what the final temperature is. So that would be TF minus the initial temperature of the cooler water, which is 10 degrees Celsius, right? And basically it's all algebra from here. So what I would do is, for example, there's several ways you can go about this. What I'll do is divide both sides by 15. I'll divide both sides by 35.0 grams. Let's do that. Divide by 35.0 grams, right? So this will cancel with that. You're going to end up with TF minus 75 degrees Celsius here. And this will be equal to, okay, so minus 1.5 divided by 35. So according to my calculation, that will be minus 0.429 times TF minus 10 degrees. And then I would multiply this right across everything here within the parentheses. So that would be minus 0.429 TF plus, so 10 times that will give you 4.29. All right, so running out of space here, let me continue here. So let me just rewrite this up here. TF minus 75 degrees Celsius will be equal to minus 0.429 TF plus 4.29. Okay, so I want to group like terms together on the same side. So what I'm going to do is add 0.429 TF to both sides plus 0.429 TF. So this will go. And what I'm going to do also is that I'm going to add 75 degrees Celsius. This should be degrees Celsius here. Degrees Celsius here. On both sides, plus 75 degrees Celsius on both sides. So that these two would go. And you're going to end up with 0.4. Oh, wait a minute. 1.042. No. 1.429 TF, and that will be equal to those two added, which would be what? 79 degrees Celsius. So that means that TF will be equal to 79 degrees Celsius divided by 1.429. So 79 degrees Celsius divided by 1.429. So according to my calculation, this works out to be equal to 55 degrees Celsius. Which makes sense if you think about it, because you start off with water at 75 degrees Celsius added to water at 10 degrees Celsius. So the final temperature must be somewhere in between, which is what we got here. We got 55 degrees Celsius as the final answer. Right? Okay, any questions about this one? Any questions? Any questions? Any questions? All right. Is it okay for me to clear this? See what we have next. You know what? I'm gonna leave this one for you to do. Let me see, number 6. Okay, I want you to try that one on your own. Because I want to go to some other topics. If you have any questions after trying it, let me know, all right? You can call me or you can Skype me, whatever, all right? Okay, so we're gonna look at some problem solving, okay. We're talking about here how to measure the enthalpy changes for chemical reactions. So as we said before, if you have a reaction taking place in a calorimeter, the amount of heat change for the reaction would be equal to minus the amount of heat change for the calorimeter because, you know, whatever the amount of heat that is generated in the reaction will be absorbed by the calorimeter, right? And the Q of the calorimeter, of course, is equal to this equation right here. So basically, if we can determine the mass, specific heat of the calorimeter and the change in temperature, and the mass of the substances involved in the reaction, then we can find the heat change as far as the calorimeter is concerned, and then put a negative sign in front of it to get the heat change for the reaction, which would be basically giving us ultimately, with further calculation, the enthalpy of the reaction, right? So we have this example right here. It says a 50 millisample of a 0.250 m hydrochloric acid solution at 19.50 degrees Celsius is added to 50.0 mils of a 0.25 m sodium hydroxide solution, also at 19.5 degrees Celsius, in a calorimeter. After mixing, the temperature rises to 21.2 degrees Celsius. Calculate the heat of this reaction. Okay, so I'm going to need some more space again. So let me copy and paste this onto. Okay. Over. So first thing I would do is to calculate the heat of reaction is to find, well, as we said before, the equation is Q is equal to M times C times delta T. Now, there are some assumptions we have to make here, and I probably should have stated it from the outset. We're going to assume that the density of the solution, I should say density of the solutions, hydrochloric acid and sodium hydroxide, is the same as the density of water, which is a very good approximation actually, 1.00 grams per minute, all right? So the total volume of the mixture is, put that down here, is the 50 mils of the acid and the 50 mils of the base, which would be 100 mils. So 50.0 mils plus 50.0 mils, and that's equal to 100.0 mils, all right? So to calculate the heat change of this reaction, that will equal to Q is equal to the mass, which is 100.0 mils multiplied by the density, which is 1.00 grams per mil, multiplied by the specific heat. Again, we are going to assume that the specific heat is that of water, joules per grams per degree Celsius, multiplied by the temperature change. So what's the temperature change? Well, the question says that the temperature was initially 19.5 and it rises to 21.2. And by the way, I should have put here Q of the calorimeter, all right? So as far as the calorimeter is concerned, there's an increase in temperature. So that increase will be 21.21 degrees Celsius minus 19.5 degrees Celsius, 0.50 degrees Celsius. And that's basically, let's work out what's within the parentheses first, 21.21 minus 19.50. And this part here, according to my calculations, this part here works out to be 1.71 degrees Celsius, right? So I'm going to take that, multiply that by 4.184 times 100. And according to my calculation, this works out to be, when you round off to 3 sig figs, 715 joules, right? So that would be the heat change of the calorimeter, which means that Q of the reaction, which is what the question is asking for, will be equal to minus 715 joules. And that's how you do it. Right? Any questions about this? Yes, sir.
Is there calibrator?
I'm sorry?
What is? calibrator?
Oh, that's the instrument that is used. I don't know if you were here when I talked about it, but a calorimeter is basically an instrument that is used to measure heat flow. So the reaction is done in the calorimeter. So that's what Qcal means. The heat change for the calorimeter is equal to that. Because the temperature rises, that means that it's positive. And therefore, for the reaction, it's negative. Right? Because the reaction is producing the heat that is absorbed by the calorimeter. All right? Okay, any other questions about this? Any other questions? Any other questions? Okay, now there's a second part, going back to the slide here. It says, express the results of the previous questions for molar amounts of the reactants and products. That is, determine the value of delta H that should be written in the equation, as you can see here. What they're asking for the delta H value here, based on the reaction. Now, based on the reaction, there's a 1-to-1 molar ratio between the sodium hydroxide and the hydrochloric acid, right? And in the question, they gave us the volume and molarity for both the acid and the base. And you'll notice that they're the same, right? So whatever the number of moles of the acid is, the number of moles of the base is. So what I'm going to do is go back to here, and I'm going to so basically, the first thing I would do to answer that question is I would find the number of moles of the sodium hydroxide, which will turn out to be equal to the number of moles of the acid. And that is equal to 50.0 mils, which we have to convert to liters, 1 liter over 1,000 mils. And then I have to convert that, I have to multiply that by the molarity, I should say, 0.250 moles per liter, right? So 50 divided by 1,000 times 0.25. So according to my calculation, that works out to be 0.0125 moles, right? So that's the moles of both acid and base. Now the amount of heat that was produced, I forgot what the answer. What was the answer? 70. What was the answer to the first part? 715. Is it kilojoules or joules? Joules, right? So that's the amount of heat released for this amount of moles of both hydrochloric acid and sodium hydroxide. So to find the delta H based on joules per mole, all we have to do is find the result of dividing 715 joules by 0.0125 moles. So 715 divided by 0.0125. And according to my calculations, this works out to be equal to 57,200 joules per mole. Let me see what the question asks for in terms of the units. Okay, they didn't specify the units, so you could leave it as joules per mole, all right? So that's basically how I would do that particular example.
What is the H when it says delta H there?
Right, H is enthalpy,
Okay,
right? So delta H is the change in enthalpy, which is basically the heat change under constant pressure conditions,
okay.
right? Okay, any other questions about this? Any other questions about this example? Okay, back to the PowerPoint. Okay, this is just some more information about the bomb calorimeter. As I said before, this is done for determining the heat change or the amount of heat released when an organic chemistry is organic compound is combusted. Please note that under these conditions, the reaction is carried out under constant volume, which is of course not true in most cases. Most cases where you're doing a reaction under normal circumstances, it's done under constant pressure conditions. In this case, however, because it's encased in this, this bulb right here, the volume is constant, right? And what that means therefore is that if you recall, we say that Q is equal to delta U plus PV or P delta V. Because the volume is constant, that means that this is zero. So that means that the Q of the reaction or the Q of the calorimeter will be equal to the internal energy of the calorimeter. All right, so basically the enthalpy of the reaction will be equal to delta U, right? As stated here, delta U measurement as a result of this is a very good approximation of the enthalpy change that is taking place, all right? Okay, and that's all we're going to say about that. Let me see here. Okay, so in the time that we have left, we're going to talk about this very important law known as Hess's law of constant heat summation. You should be able to at least make a big dent in this particular topic. Okay, so of course, we can write down pretty much an equation representing any reaction, but sometimes those reactions simply won't occur or you cannot perform those reactions for many reasons. A lot of practical reasons does not allow for you to carry out a specific reaction, right? And therefore, if you cannot carry out that reaction, then you cannot make certain measurements about that reaction. And that is also true when it comes to enthalpy changes, right? If you cannot carry out the reaction, then you cannot determine the enthalpy change of the reaction. However, you can determine the enthalpy of the reaction if you know the enthalpy changes for other related reactions. And we're going to see how that works. So let's look at this example. Let's look at this reaction between carbon and oxygen to form carbon monoxide, right? Very simple reaction, which does occur, right? The problem, however, is that if you try to measure the delta H of this reaction, or I should say, if you try to do this reaction, it's very difficult to stop the carbon monoxide from itself reacting with another oxygen molecule, right? So therefore, it's very difficult to just stop right here, right, and end up with this product without the carbon monoxide reacting with more oxygen to form carbon dioxide, all right? So because of that, we can look at other related reactions to determine, at least by calculation, the enthalpy of that reaction between carbon and oxygen, right? Key thing you need to remember is this: enthalpy change is a state function. And like all other state functions, the change is independent of how many steps you have to carry out to get from the reactants to the product, all right? And this brings us to Hess's law. Hess's law says that if an equation can be expressed as the sum of two or more other equations, the enthalpy change of the desired equation is the sum of the enthalpy change of the other equation, all right? So I'm just going to illustrate this first using a hypothetical example, and then we're going to get to a real example. So here's a hypothetical example. Let's say, let's get rid of all this here. Let's say that you have this reaction, A going to C, right? And let's say the enthalpy change of this reaction is delta H3, all right? Let's say you can get from A to a product B, and then from B to C, right? So let's say for A to B, the enthalpy change is delta H1, and let's say that from B to C, the enthalpy change is delta H2, right? What Hess's law is saying is that it doesn't matter if you go directly from A to C or from A to C through an intermediate B, the enthalpy change will still be the same. So therefore, as a result, we can say that delta H3 is equal to delta H1 plus delta H2, right? So that's the relationship between those three enthalpy changes, right? And basically, if you know two of those terms, then you can find out what the third one is, right? And that is what we exploit in order to find out the enthalpy change of a reaction, which may be difficult to determine, but if we know the enthalpy change of other reactions that are related, then we can do a simple analysis to get the enthalpy change that we're trying to find. Let me show you another way of looking at this. So I'm going to write down A going to B, and the enthalpy change of that is delta H1, and then B going to C, and the enthalpy change of that is delta H2, right? So if I add these two equations together, right, the B's will cancel out, you're gonna end up with A going to C. The delta H for that particular last net equation is going to be equal to the sum of these two. So delta H3 will be equal to delta H1 plus delta H2. So this is another approach which shows you the relationship between these delta H values. All right. So this is your hypothetical example. So we're going to get to a real example. Going back to the carbon monoxide situation, right? So another way of showing how this works, using a real example. So we start off with carbon, right? We want to find out the enthalpy change for carbon being converted to carbon monoxide, right? So carbon will react with half a molecule of oxygen to form carbon monoxide, right? This is what we need to find, right? Very difficult to measure in practice, because as I said before, the carbon monoxide itself can react further with any oxygen around to form carbon dioxide. So what do? Well, we know that to go from carbon to carbon dioxide, the enthalpy change is minus 393.5 kilojoules. We also know that to go from carbon monoxide to carbon dioxide, the enthalpy change is minus 283.0, right? So therefore, using Hess's law, basically we can conclude that this enthalpy change will be the sum of this plus this, right? So to find delta HA, we have to subtract this value here from delta HC, and that will give you the enthalpy change of the reaction, all right? So if I were to represent it in another way, similar to what I showed you earlier, E solid plus O2 gas, half O2 gas, will give you CO gas, right? I'm just going to call this delta H1. You can use the numbers that I gave you earlier. And then CO gas plus another half molecule of oxygen will give you CO2 gas. And the delta H for that would be delta H2, right? So if you were to add these two equations together, like I showed you in the hypothetical example, the intermediate that will cancel out would be the carbon monoxide. So you're going to end up with C solid plus half give you one oxygen molecule to give you CO2. And therefore delta H3 would be equal to, in this case, delta H2 plus delta H1. All right. So to find delta H1, which is what we were discussing in relation to the formation of carbon dioxide, delta H1, based on this equation here, would be equal to delta H3 minus delta H2. And that's basically how Hess's law works. All right, so even though we could not in practice, or it would be very difficult for us to do this reaction and determine delta H1, we can find it based on the enthalpy changes for other related reactions. All right. Okay, any questions about this example? Any questions? Any questions? Okay, I think I'm going to stop here because the next slide involves questions which will take some time for me to we're going to look at this question. We're going to apply what we just learned to this question next class. So that's the very first thing we're going to discuss next class, all right? All right, so that's it for today, folks. Here. Okay, you guys.